back, welcome back, welcome back. All right, so so here we're going to start with multiple linear regression. Yeah, everyone has experienced multiple linear regressions where you have multiple explanatory variables rather than just one, and how to do this within R. So do multiple body measurements predict penguin's body mass? Okay. Can we model body mass using multiple explanatory variables, flipper length, right? More detail, build length, and build depth. So that is the question at hand. The primary use, again, we're going to use multiple explanatory variables to not only explain the variability in the response, but also use it to predict it. Okay. Summary statistics. I just provide the correlations because you have to implement matrix analysis to find the regression coefficients, not just simply correlation in the mean to the standard deviation. So I just provide the correlations. Okay. And it obviously seems as if the correlation between flipper and body mass is pretty high. But the visualization is so telling. So I'm actually going to go into the visualization. But this free X, I'm pretty sure you might have done this in ChatGPT. I'm just going to copy this and remove it. And everything else is pretty much the same except for this pivot. This is actually really interesting, okay? So what you're able to do with this particular pivot is have, let me show you. Let's just call this temp df or pivot. Let me do it better so that you all don't practice. Pivot penguin df, right? And then let's look at this data frame. So each body mass, because I didn't select that, it's correlated with that particular body mass is correlated with that particular value for. So this person, or at least this penguin, is having, it shows up 3 times because it's showing a relationship between each one of these quantitative variables. Now that's a huge use of the pivot longer, right? So we now can create 3 different visualizations based off of one response variable and 3 different measurements. Okay, so that's pretty cool there. So I'm going to remove that and then go back here, and then I'm going to show you something that looks quite bad. All right. So this looks very horrible because you really can't see the relationship. And the reason why it's doing this is so that each of the explanatory variables has the same scale. But if I were to put this back, scales free, it's going to allow it to have its own x-axis, its own scale corresponding to the explanatory variable. So, boom, looks better. Woo! Something's going on. I know something's going on here, and I'll argue this is probably 2 different species. Okay. So that's what we're seeing here, but obviously, regardless of the explanatory variable, flipper, build length, build depth, it has a linear relationship with body mass. Okay, it does. Okay. So let's do the easy way. So the first easy way is going to be the same thing. So we do MLR, LM. We specify the response variable, body mass, G, and I don't remember the other ones. So then it's going to be these variables, boom. But this time, they're not going to be commas. They're all still just going to be pluses. Okay. Plus, comma, data is equal to penguins. Okay, so then not summarize, but summary. Oh, I'll call this MLR model. And then I'll do summary of MLR model. And then boom. Okay, I'm given, oh, look at that. And so it's because the strength between flipper length and body mass is so strong, it's clouding these other 2 relationships. That's why this is not suffice, but you should look at the visualization. Because it's obviously a linear relationship. Okay. Um, so there's more modeling that can be done. If we were to do more regression, we would see the residual versus fitted plot, and I would argue that there should be a pattern in that. So that is the old way of doing things. The new way of doing things, I'm going to do a little bit of a copy paste just so that we can make our lives a tad bit easier. And so we're going to do it here, copy paste this. The only thing we have to add is not just slipper length millimeter, but we should add also these are the two variables. Add them. Okay. And then when I run this, I'm going to get, I should get the same regression coefficients, okay, as before. 5420, 5420, negative 60, negative 6000, negative 6400. There we go. Okay, so that's that. And then if I want to get those model metrics, oh no, my alarm again. Stop. Okay, sorry. So then we go, here we go, paste this, and then we just now see the model metrics. They're not going to be exact. For some strange reason, I didn't get to do my diligence. They're not exact, and I think this is providing you the R squared, not necessarily your adjusted R squared. Sorry, right here. But that's the new way of doing the tidy model. Okay? That's that. That's fine. So the next huge thing, okay, I'll say, is there any questions? But I can't hear. We can put it in the comments, you know. And I actually get emails saying I get comments, so it's interesting. So does the relationship, excuse me, between flipper length and body mass differ by species? So this is a little even more different. This is, I'm gonna highlight the variables that I didn't highlight before. But here we can actually specify there's two explanatory variables, flipper length and species, but species this time is categorical, whereas in this previous example all the variables were quantitative. So when we do this, the idea is the interaction variable model to include different different groups when it comes to predicting the response variable. So I did a group by, but then I also did it by species. I did a group by species, but I want to see the correlation based on species. I think there should be 3. Yeah, there should be 3. And obviously, like this is very telling, right? In that all 3 of them have 3 different correlations. So most likely the slopes are different across all 3. The regression coefficient for the relationship between the explanatory variable and response is going to be different. Okay. So with that being said, anything important for me to highlight here? Not so much. Color, okay, not so much. It's pretty much the same. So then here, I did do alpha is equal to 7. That controls the transparency. But here we have Gen 2 up here, as we saw with Monolea Nova and Adelaide, and Chinstrap down here. Okay, not too crazy. But we obviously see that these have different slopes. An interaction model allows us to test for different slopes as well as different y-intercepts. I don't know if the difference in y-intercepts are going to be significant, but I can tell you that at least this slope is different from these 2 slopes. Let's see our analysis. Again, MLR enter. Okay, assign LM. Nice little function. Body mass G tilde, what's the next thing? Species, and this time for interaction you do time, so it's not plus, it's going to be times flipper length. I think it's just flipper length comma data is equal to penguins. And then summarize using the summary function MLR enter. I'm gonna call this enter model just so I can be consistent. Oh, we're at 10. That's good. We're at 10. Boom. Ah, sorry. Damn. All right. And the thing is, I'm not spending time talking about the p-values here. I'll do it. I want to do it kind of here. So this is something there's difference in our y-intercept is different from 0, but again it has no meaning because you can have a negative body mass. Same thing when it comes to these values, but they're telling me that chin strap in our reference group, which is it's not labeled chin strap. Adelaide is our reference group, and so chin strap and Adelaide are not different, but Gen 2 is different. Like we see here, Gen 2 is up here. Adelaide and chin strap have similar y-intercepts. We don't have evidence to reject the hypothesis. Then here, this is telling me that across all three, in terms of Adelaide, we know that this is significant for Adelaide, this pink one. This tells me that there's no difference between chin strap and Adelaide in terms of slope. But this, sorry, I'm looking at the p-values at the same time. So this one is not different from Adelaide and chin strap, but this one tells me that this is different. Gen 2 is different from Adelaide because of p-value. Okay, cool. With the same logic here, a little bit of a copy and paste, right? Copy, paste, and then multiply. Which one was it? Flipper times species. Right, the same values and the same p-values, which is good. Okay. And then we can just copy and paste again here. And you don't have to do anything else with it because it's the same model fit, augment, data, body mass, okay, boom. Okay, the numbers are not exactly the same, but there's some difference in calculations. Real fast. I'm not going to show the analysis, but logistic regression, if you haven't seen it or heard of it before, is you're predicting a categorical binary variable with a quantitative response, or even a categorical variable, okay, or categorical binary variable. So you just have anything on your x as your x, but your response variable legitimately is going to be categorical binary. And so what you're trying to do here is determine its sex based off of body measurements. And I think we're going to use flipper length of in millimeters. Okay, so if I just see this, see the frequency of both genders, or both sex, sorry, and then I'll visualize it. Okay, and this visual is nice and cool, but there is a more accepted way of visualizing this data, and it's utilizing the sigmoid function. That's neither here nor there. But we're talking. Well, actually, we're going to talk more about that next, in a way, in our next section. But we're not going to do the analysis. I'll provide a summary, and yeah, thank you for watching. I want to talk more, but it's fine.